And then I accidentally.
Okay, I'm going to get started. My name's Tim Gorringe. I'm going to be the instructor for the lecture part of this class. So you probably met your recitation instructor yesterday, and you might or might not have met your lab instructor yet, but you'll meet your lab instructor this week. We're kind of a team in organizing this class, this course. If you want to contact me, I have an office in this building. It's room 309. So it's not quite above, but almost above the bagel shop. So on the third floor. You can email me. The best email for me is started to call myself tim.gorringe at uky.edu. But I don't think you really need the dot. That's better than communicating through, I'll talk about this later, WebAssign, because I don't always see it. And better than communicating through Canvas, because I see it immediately here. My office hours, I posted them on the slides, so they're Mondays and they're Thursdays. On Mondays they're at 2:30 to 3:30, and on Thursdays they're 1 to 2. You can always make an appointment for another time, or you can always drop by at another time, and we can always do a Zoom or a office appointment. So I wanted to say a few things first about the organization of the course. I'll say here some of the materials that you need, but then also how the course is structured and the course is graded. And then we'll move on, and I'll say a few words about the overall content of the course, what we're going to learn this semester, and then we'll get on to some material for today's class. So the things you need for the class, obviously you need access to Canvas. So on Canvas is posted the assignments for the class, posted the grades for the class. I post my lecture slides and videos on Canvas. So you need access to Canvas. Of course you have access to Canvas. You'll need access to the textbook, which is College Physics, Survey and Boole. I'm guessing that most of you had that same textbook for Physics 211. And you'll need access to the WebAssign homework system, because that's how we collect the homework. So I think the most economic way of getting those two things, because you have to pay for those two things, the access to the textbook and the access to the WebAssign service, is through the first aid program. So there's a link, you should see a link on our Canvas page, and I think it's $47 to sign up for electronic textbook access and the WebAssign homework access. If you wanted a hard copy of the textbook, then you could, a new hard copy of the textbook is very expensive, but you could always get an old second-hand copy of the textbook, and it could be edition 11, or it could be edition 10 or edition 9, because they're almost the same except for the numbering of the problems. So the MyUK, the first aid program gives you the electronic version of the textbook and the WebAssign homework service. Okay, so the class will operate or work on a weekly cycle. So there would be a repeating weekly cycle from this week onwards to the end of the semester. The way the weekly cycle will work is that we'll have a Tuesday lecture, and we'll introduce some new material. We'll have a Thursday lecture, and we'll introduce some new material. You'll then have your Monday recitation, which involves a worksheet that's based on that material. And you'll also have your WebAssign homework due, which is also based on that material, and that's due at midnight on Monday. So that's a weekly cycle. And most weeks follow exactly that cycle, that you get 2 lectures, Tuesday and Thursday of new material, and then you get experience working on that material in the recitation, and you can use that experience on that material for submitting the homework. There are a few exceptions to this weekly cycle. For example, if we have a test, we've got 3 tests, 1, 2, and 3. The recitation prior to the test will be actually a test review, a practice test. So that will be a difference. This is how your grade's going to be calculated in the class. This lists all the components, parts towards your grade calculation and the proportions of those different parts. So I just wanted to go through this table a little bit. This table is or a version of this information is in the syllabus. But if you look here in red, these are the different components that go into your grade. So the biggest contribution to your grade is from 3 in-class tests. So I think in some date in February, we've got a test. Some date in March, just before spring break, we got a test. And then there's a final test at the end of the semester. These are testing 3 distinct parts of Physics 2.13. So there's those 3 tests, and together they add up to a little over 50% of your final score. So that's the biggest contribution. Those tests kind of test the different ways we go about problem solving in physics. Sometimes we're just conceptually solving problems, understanding them, so that there's a true force conceptual part on the test. It's worth 20%. Most of the time we go about physics problem solving by calculations and numerical solutions, and that's the largest part on the test. That's 80% of the test. And so that's how the tests work. The remaining items here, so these add up to a little less than 50%, just under 50%. Well, there's going to be quizzes in lecture. There's your WebAssign homework. There's your recitation worksheet. And then there's your lab work. Each of those 3 things in different ways is designed to prepare you for the test. So in the lecture quizzes, right, I'm going to give you little quizzes, give you a few minutes to think about them, and they're on concepts, and that comes up on the test. In the homework and the worksheets, you'll get experience with your physics problem solving, your critical thinking, and your calculating and numerical solutions to physics problems. So they help with that, preparing for that part of the test. And then finally the lab, well, the lab gives you practical experience with the topics that we're covering on the test. So you get a sort of hands-on experience with the test material. So each of these items, the quizzes, the worksheets, the homework, and the lab, are trying to put together in different ways experience for you that will help you with the test material. To calculate your final grade from your final score, I've got a 15 a 15-point scale. So that means if you're in the top 15%, 85% to 100%, that's an A grade, guaranteed. If you're in the next 15%, so that's 70 to 85%, that's a B grade, and so on. So that's the scheme for finally turning the scores that you've accumulated in all these different assignments into a final grade in this class. Okay, if you look in the course syllabus, at the back of the course syllabus on the Canvas page is a schedule. So that schedule is kind of a detailed schedule of class by class and week by week. So in that schedule, you can see the various topics that we cover in each lecture class. This is just a bit of it. Now, I cut out this piece because this piece here shows your path, our path, from now, this moment, to test 1. So today's class, we're going to talk a bit about electrical charge. And then we're going to continue with all these other topics in electricity. And on February the 8th, apparently, we've got a test on all those topics in electricity. So that material will be tested then. These are the section numbers in the textbook. So, the best way to prepare for lecture is to read these section numbers ahead of time. This red and blue labeling here, this is not in the, this is not from the course schedule. I just added this. I added this because I wanted to clarify something. As I said, normally on the Monday that follows, say, a Tuesday class here on January the 16th or a Thursday class on January the 18th, there'll be a recitation worksheet and there'll be your web-assigned homework due. So this is normal. And this is normal, and so forth. This is normal too. Yesterday for you wasn't normal. I gave you a worksheet, and you didn't even have a class. So that was kind of unnormal. But that worksheet doesn't count for credit, so you don't have to worry about that. That worksheet the idea was to remind you of a few important things from 211 we're going to use in 213. Next week's a little strange too, because I've got next Monday is Martin Luther King Day, so there is no class, there's no worksheet, but I got the homework due. So the homework is due from today's class and the next class. That homework too is not counted for credit, but I would definitely get into the rhythm of using WebAssign and submitting that homework. Okay. Oops. Any questions on all that? That's the organizational part. Yes?
Is the final cumulative?
No, that's actually a very good question. I was thinking of that question myself. No, it's not. The course naturally breaks into, I'll describe this in a moment, 3 distinct topics. And so test 1 tests the first topic, test 2 that second topic, and then test 3 is just the last third. Yeah, so that's a very good point. Any other questions? Okay, then I'll move on. Course overview. What I mean here is I just got, I think, a slide or two just to give you a feeling of what we're going to cover over the entire semester. What is the content of this course over the entire semester? This is just, I think, an advertisement to try and get you back to class after syllabus week. So we're going to see what we're going to cover throughout the semester. Okay. So on this slide, if you look down in the bottom left corner, that's really the smallest scales that we've explored, that scientists have explored. It's the size scales of the atomic nucleus. And in that landscape, nuclear forces are kind of king or queen. On the top right, that's a galaxy. And the scales of galaxies are the greatest scales that the largest scales that we explore. And that's where gravity is king or queen. But in between the size scales of the smallest objects we've ever explored, so nuclei and smaller, and the larger objects that we explore, sort of astronomical scales of objects, in between there is our everyday lives, right? I mean, we don't normally see this scale of nuclei. We don't normally see this scale of galaxy. Our everyday lives are in between. It's this vast region in between this very tiny bookend and this very, very big bookend. In that region, there's one force that's king or queen, and that force is electromagnetism. And in a sense, this entire course is about electromagnetism, about the electromagnetic force. And so that's the content in one word of the course, electromagnetism. Now, electromagnetism actually breaks down into different phases or different parts. And so, as we go through test 1, test 2, test 3, we'll be looking at different phases, different parts of electromagnetism. Electricity is one part. Electricity is interesting and important because electricity is kind of the glue, the force that holds atoms and molecules together, for example. So it's very important in constructing our everyday world. The periodic table is built on the electrical force. Without the electrical force, we wouldn't have periodic table. The electrical force, electricity is how kind of cells work. I don't really know much about that stuff, but cells work electrochemically. So they're electrical devices. Neurons work electrochemically. They're electrical devices. And actually, things like your brain, my brain, your heart, my heart, they're electrical devices built out of electrical components. So we're electrical, right? Even your, and even my, no matter how bad or good they are, our thoughts, our emotions, our dreams, they're all ultimately electrical in nature. And so understanding electrical forces is important. Okay. Magnetism. So I don't know if you know this, you probably know it, that we live on a magnet. The Earth is a huge magnet. And that's kind of interesting and curious that the Earth is a big magnet. But it's more than actually interesting and curious that Earth's a big magnet because it saves our lives. Because the Earth's magnetic, it provides a shield, a magnetic shield of us from radiation, deadly radiation from outer space. Without the Earth's magnetic field, on Earth there would, I presume, just be like cockroaches and beetles that could survive the deadly radiation. So we have to thank Earth for its magnetic field because it's how we survive. Magnetism is also important because essentially our whole modern, comfortable, technological lifestyles is built on magnetism. The way that we generate electricity that drives everything that we're using, from the lights to the computers. The way that we generate electricity is by harnessing magnetism to harvest electricity, electrical currents. And so it's very, very important from a practical modern lifestyle perspective. So that's why we might be interested in magnetism. What about light? Is light interesting? Well, there's a couple of reasons light is very interesting. Light turns out to be built out of electromagnetism. We're going to discover that, but it was only recently in like 150 years, so not really recently, but fairly recently figured out that light, what is light? It's actually a bundle of electricity and magnetism, a propagating wave, an undulating wave of electricity and magnetism. So light emerges from the theory of electricity and magnetism. So that's very interesting. But also light itself is very important. You know, sunlight is the most important light. Without sunlight, again, we and everything else living on Earth would be dead. Because sunlight brings Earth energy from the sun. And it's harvesting that energy that allows, you know, plants and trees to grow. It allows us to grow and live. So light is important too, especially sunlight, and so we'll explore that. Finally, the last thing that we'll cover here, turns out, and again, this hasn't really been known for very long, the scale of 100 years, that matter, all matter, you know, the chair or the table, but you or I, we're all built out of electrical building blocks, electromagnetic building blocks. And so towards the end of the class, we're going to turn our understanding of electricity and magnetism back onto matter. Once we know how electricity and magnetism works, we can turn that understanding onto matter and understand the nature of matter, get a deeper understanding of matter. We'll also, this might seem strange, we'll be able to turn that understanding of electricity and magnetism back on space and time. We all have notions of space and time. Well, we'll turn the theory of electromagnetism onto our notions of space and time and really figure out that our everyday notion of space and time isn't quite correct. Really, space and time are connected together. They're woven together in a kind of four-dimensional space-time fabric that is stretchable and squeezable. And so we'll discover that by turning our theory of electricity and magnetism onto space and time itself. Okay, so that's the content of the semester. Any questions on all that? In which case, I'll actually start the class then. So in today's class, I want to cover an introduction to electricity. And I've kind of listed the components of an introduction to electricity on this slide. So I want to start with the discovery of electrical attraction and electrical repulsion. That's where electricity began, and it began thousands of years ago, 2,500 years ago. I want to introduce the understanding of the electrical attraction and the electrical repulsion. And that introduces a new property of nature, dimension of nature, that's called electric charge. So I'll introduce electric charge. I want to then talk about this modern realization that all matter, chairs, tables, you, I, we're all built out of electrical building blocks. And so I want to talk about that realization that we live in a world which is constructed out of electromagnetic building blocks. And then I finally want to talk a little bit about the first steps in harnessing electricity for our modern technological lives. So the steps we'll see today are kind of baby steps in that. And over the semester, we're introduced more and more of the discoveries that led to, you know, our modern, comfortable lifestyles. So this is the goal for today. Okay, so first topic was just the observation or the discovery of electricity and electrical attraction and electrical repulsion. So let's talk a little bit about that. So I made a few bullets here that kind of actually cover about 2,500 years of the discovery or the observation of electrical attraction. So the first documentation of electrical attraction goes back to, everything goes back here, ancient Greeks. They documented electrical attraction. I think it's because, you know, much before ancient Greeks, nobody could write anything down to start with, and ancient Greeks were the first that really thought, well, you know, if I think this or that, I'll write it down. And so we have this record of what they were thinking about, and they observed electrical attraction. Actually, they observed a very narrow window on electrical attraction. So they observed that amber, a material called amber, it's like a resin, hardened resin from a tree. If you rub amber, then it will attract straw or hair. Now, they rubbed amber because amber was kind of jewelry, used as jewelry. So I guess you want to look good if you're going to the party. And so you rub your amber and you realize that it's attracting your hair or straw in your hat or whatever. And so that was the first documented, written down observation of electricity. So that was a breakthrough. And that was 2,500 years ago. And basically, that didn't change much for about 2,000 years until William Gilbert. So William Gilbert was an interesting person. He was the doctor to Queen Elizabeth, not the recent Queen Elizabeth, but the much earlier Queen Elizabeth. And so that was a very prestigious position, I presume, although she did die rather young. But anyway, he was her doctor. And he was not just interested in medicine, but he was interested in all sorts of science. He was interested in magnetism. He was interested in electricity. And he discovered, actually, that it's not just amber that if you rub it will attract straw or hair. It's actually pretty much anything. If you rub it, it can attract straw or hair. So this idea that amber was something special, there's nothing special about amber. Most materials, and we'll see some examples of it, if you rub them, then they can attract electrically light objects like hair or straw. So that was a big contribution. That maybe doesn't sound like too much, but it expanded the field of electricity from this tiny, narrow amber business to this, well, everything seems to be electrical. Everything seems to be able to attract electrically. So that was a big breakthrough. And another breakthrough I've listed on this slide is by Dufay. So Dufay, also an interesting person. I think he was some French nobleman. He had a lot of time on his hands, presumably. And he also was interested in science and interested in magnetism and interested in electricity. And he made a very, very important discovery. So what he discovered was there's not just electrical attraction, but there's also electrical repulsion. That electricity has two kind of flavors to it and how it works. It can both electrically attract and electrically repel. That's quite different from gravity. Gravity always attracts, never repels. And so that was a huge, huge breakthrough. I'm going to show you a demonstration of electrical attraction and electrical repulsion. Now, normally I would try and do it as a, I'm not going to show you a demonstration actually, but I would normally try and demonstrate it with, I have a glass rod, I have a plastic rod, two different materials, and I've got cat's fur and I've got silk also. And so I can charge up the glass rod or charge up the plastic, the rubber rod with the silk or the cat's fur. And I can make these two circumstances where if I charge up two glass rods, they're kind of the same material, you'll see repulsion. If I charge up two plastic rods, same material, you'll see repulsion. But if I charge up a glass rod and a plastic rod, then you'll see attraction. So I could try and demonstrate this right now, but it doesn't work when it's raining. So it's not going to work very well. It doesn't work when it's raining. I can tell you the reason why. You might know this. Air can be a conductor of electricity and it can be an insulator of electricity. Dry air is a good insulator. And this experiment, this demonstration works with dry air. Wet air is a conductor. It's a poor insulator, and this experiment doesn't work very well with wet air. So with that in mind, I actually I'll show you videos of it when it was dry on Monday. I wanted to show you something rather that you might think, this is stupid. So show you something stupid first. I want to show you, I'm going to take two rods and I'm not going to rub them to charge them up. And I'm going to show you, at least to begin with, if you do that, they don't attract one another. So that's sort of like a control experiment. So here I've got a glass rod, and I'm not going to rub it with the cat's fur, and I'm not going to rub it with the silk. I'm just going to put it on this turntable where it's free to rotate. The turntable will help me see the forces that are acting on the rod due to some other rod, for example. So here's the glass rod on the turntable. I've got another glass rod. I'm going to bring that up. And look, I'm putting it next to the other glass rod on the turntable. There's no forces. There's no electrical attraction. There's no electrical repulsion between an unrubbed glass rod and another unrubbed glass rod. Now, that might seem kind of uninteresting, but there is something very interesting about it. Inside the glass rod, as you know, right, there's a lot of positive charge and a lot of negative charge associated with the electrons and the protons inside the glass rod. If you just thought about the electrical interaction between the electrons in one glass rod and the electrons in the other glass rod, that electrical interaction, that electrical force is so large, it would, if they just interacted on their own, it would destroy this room. We'd all be dead. The whole building would be disintegrated. The force between the electrons in one glass rod and the other glass rod is so large, it would be completely destructive. Likewise, the force between the protons in one glass rod and the protons in the other glass rod, that's also enormously large and would be destructive, explosive. The reason the two glass rods don't explode and destroy us all and destroy the building is the fact that there's equal amounts of this enormous attraction and repulsion between the two glass rods. So there's repulsion due to the electrons in both rods and the protons in both rods. But there's attraction due to the electrons in one rod and the protons in the other rod, and the electrons in the other rod and the protons in the first rod. And those enormous forces actually absolutely perfectly balance out. And so we survived that demonstration. We survived that demonstration, not because there's no forces there. There's actually enormous forces there, but they're perfectly canceling out. So it really reminds us that electricity is a hidden world. It's a hidden world of a monster force, and we don't normally see that monster force because it's normally in perfect balance with attraction and repulsion canceling. Okay. I mean, it still wasn't an exciting video, but okay, so this time I'm going to actually, rub the glass rod with the fur, rub the plastic or the rubber rod with the silk. I'm going to charge them up, and we're going to see these two examples of electrical attraction and electrical repulsion. So this is a glass rod that I've charged up, and then I've got the same sort of material, another glass rod I'm going to charge up. So this means you've got two glass rods with the same type of electrical charge, with two same materials, and they're going to repel one another. And that's what we just saw, right? I brought the first glass rod up to the second glass rod. I didn't touch it whatsoever, but it ran away. It ran away from that first glass rod. So now I'm going to do it with the plastic rod. So I've got two different materials here, now both plastic, and I'm going to rub them to charge them up. I put one on the turntable so that we can see it move under forces. I'm going to get the second one. I'm going to charge that up, and I'm going to bring it close but not touch the original one on the turntable, and we're going to see the electrical interaction between them. And here again we see repulsion. I'm repelling, the one rod is being repelled by the other rod. Now I'm going to do the third case, right? We've done glass and glass, they repelled. We did plastic and plastic, they repelled. The last case I'm going to do is plastic and glass, or glass and plastic, opposite materials. So now I'm going to charge up with the silk, the plastic, put it on the turntable again so we can see if it experiences any forces. I'm going to charge up the glass. Where did I go? Found my way back. Charge it up with the cat's fur, and let's see what happens here. I'm going to put the glass near the plastic. And now you see attraction. And so that's electrical attraction. So that, what we just watched there in those videos, you can think of that as a sort of compressed version of 2,500 years of discovery of electricity. What we've discovered is that there's electrical attraction, there's electrical repulsion. You see electrical attraction when you've got unlike objects. You see electrical repulsion when you've got like objects. And also, it seems like anything, glass, plastic, whatever, can be electrically charged, can exhibit these electrical interactions. So I want to talk now about the explanation, the detailed explanation of what's going on there. And this will introduce, I have mentioned charge, but I now really want to introduce the idea of charge. So the idea of charge is that, electrical charge, is that it's the source, the origin of the electrical attraction or the electrical repulsion between the the glass rods and the plastic rods. So they attract or repel because of a property of nature, what we might call a dimension of nature, called electrical charge. It's the source of the origin. It's the understanding of the electrical attraction and electrical repulsion. So on this slide, I'm going to try and describe so now I've jumped to modern day times when I can explain this in terms of electrical charges, positive and negative electrical charges. Actually, I can explain it in terms of atoms and molecules that the materials are made up of. Of course, if we went back, hundreds of years, thousands of years, they didn't know about atoms and molecules. They didn't know about charge. They only could say that there was electrical attraction and repulsion. So this is a modern understanding. Okay, first of all, the glass, the plastic, the fur, the silk, all those things that I was either rubbing or doing the rubbing with, they're all made of atoms and molecules. All those materials, all those atoms, are made out of charged building blocks. And of course you know these charged building blocks because you've all done chemistry. They're electrons, tiny light building blocks of nature. They're the negatively charged building blocks. And there's protons. They're kind of like the heavy, the Oompa Loompa parts of building blocks of nature. And they're positively charged. And so the first bit of the understanding is that that glass rod, that plastic rod, that fur, that silk is made out of atoms and molecules, which themselves are made out of building blocks that are have electrical charge, have this characteristic, this property, electrical charge. The electrons carry negative charge, and each one carries the same size electrical charge, 1.6 times 10 to the minus 19 coulombs. Each proton, they're the positively charged objects, each one of those carries the same amount of charge, 1.6 times 10 to the minus 19 coulombs. Okay, so that's the starting point. What's the effect of rubbing? Why am I rubbing silk on glass? Or why am I rubbing cat's fur on plastic? What's all this rubbing that's going on in this class? The purpose of the rubbing is that I'm actually scraping off electrons. So they're the kind of light building blocks that are much freer to move around. I'm scraping them off one material onto the other material. So it might be right that glass has a greater attractiveness to electrons than cat's fur has to electrons. So glass, if I rub glass with a cat's fur, it will collect more electrons. Some will leap over from the cat's fur to the glass. It might be that plastic, for example, plastic has a lesser affinity for electrons than, say, the silk. So in that case, if I rub the silk on the plastic, then electrons want to go to the silk. They jump off the plastic rod onto the silk. So I'm charging by rubbing. I'm scraping off electrons from one material and depositing them on the other material. That's how we charge objects up. And it's based on the fact that all those objects are made out of charged bits, and we're just going to move some from one material to another material because it has a greater affinity for one material than another material. So that's how charging works. Now, just to give you an idea, there's a huge number of electrons in the glass rod, in the plastic rod, in the cat's fur, in the what's the other thing? Forgotten it. Silk. We're only scraping off a very, 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 very tiny fraction. We're only transferring a very, very, very tiny fraction. It might be millions or billions of electrons in number, but that's actually a very, very, very tiny fraction and a really rather tiny amount of charge. By doing so, now after rubbing this glass with the fur or the plastic with the silk, one object has got more electrons than protons, the other one's got less electrons than protons, and so one is going to become negatively charged if it's got more electrons, the other one's going to become positively charged if it's got less electrons. That's how I create objects with positive and negative charge, by creating objects through rubbing with excesses or deficits of electrons. So that's how I generate the different charges. And then what we discover is that you get electrical repulsion when you've got two like charges. So if I have two negatively charged objects with which means excesses of electrons, they repel one another. If I have two positively charged objects, that means deficits of electrons for both of them, then they repel one another. And on the other hand, if you've got a positive and a negative object, so one object with an excess of electrons, one object with a deficit of electrons, they will attract one another. That's how you get electrical attraction. So in short, if you have the same charges, I would say like charges, so both pluses, both positives or both negatives, that's repulsion. If you have unlike charges, a plus and a minus, or a minus and a plus, that's how you get attraction. So that's the explanation of electrical attraction and repulsion in terms of positive and negative charges. That's a massive breakthrough to understand that. You might know, you might not know, that you think of Benjamin Franklin as a politician, I guess. But actually, he was the one that came up with the idea of positive and negative charges and explaining this. He was also a scientist. It's sort of amazing, really. It would be like thinking, well, Al Gore, he's a politician, and believing that he invented the internet, So in that day, people were doing all sorts of things. You had famous politicians that were also famous scientists. I don't know so many cases of that now. Okay, going on too much. This is just a graphic of what I've described, right? This is just a cartoon of what I've described. Here's on the left, right, this is the plastic or the rubber rod, which has an affinity for electrons, likes electrons. Here's the glass that not so keen on electrons. So when I've rubbed the rubber and rubbed the glass, this rubber has become negatively charged because it's got excess of electrons on it. The glass positively charged because there's an electron deficit on it, and they're going to attract one another. And then over here, this is the example on the right of electrical repulsion. So this would be rubber and rubber, or it could be glass and glass. The rubber, when I've rubbed it with the silk, has become negatively charged, got more electrons on it. Both of them have more electrons in it. So they're like charges, so they're going to repel one another. Oh, got a quiz. Okay, so this is practice quiz. This is not going to count for class credit. But it's mainly it's practice for you that that you can do the quiz and figure out the mechanics of doing the quiz. More of a practice for me, right? It's practice that am I capable? Yeah.
Why is it that the positive charge prefers the glass rod?
Oh yeah, that's a fantastic question. Why is it that positive charges prefer glass and all these combinations? That is a truly, truly complicated question of why a particular material, you think of a whole spectrum of materials, why each one of them has this or that preference for electrons. People make up tables of electron affinities that describe, there's like some material that likes the electrons the most. There's some material that likes the electrons the least, and there's a bunch of materials in between, but there's no way of really predicting exactly how much a particular material is liked or disliked by electrons. So it's a great question. There is no words I can say to say why glass likes electrons more, why rubber likes electrons less. It's an observation. It's a fact of nature. Okay. So this is how I give the quiz. They're going to just be Canvas quizzes, and I'm just going to publish them. I'm not great with technology, so let's see if we can do this. The time now is on my, oh, wow. Look, I guessed it would be 10:20, and it is actually 10:20 on here, but I've got to give you some time to do it, obviously, so I'll give you to 10:23, which I will normally give you a few minutes. Now, I'm not really worried about giving you enough time for this class because it's not going to count towards your grade. So, you know, don't be thinking, you didn't give me enough time. I wanted to really think it through and imagine what electricity is like. Let's just see that we can all do it. So I hope that you see the published quiz, and I can see you all looking down at your iPads, which makes me think that we published the quiz. And you're free to chat. You're free to talk. You know, like, I think this or you think that. Figure that out between all of you. So that's the way to do these quizzes. It's group work.
I was confused. I was like, why are you asking? Like, there's no way you're actually asking. What you were asking. Doesn't matter. I know you'd be How did you see somebody miss?
Okay, I'll get started again. So the correct answer to this, if you rub glass with a silk cloth, right, one's going to want electrons more, one's going to want electrons less. I'll be frank with you. I can never remember, you know, whether glass likes electrons more and silk likes electrons less, or which way round it is. But what I do know, well, I can't remember that, I can still answer the question. Because I know that if one of them gets more electrons, the other one must have a corresponding deficit of electrons. So I know, without knowing which one likes electrons more or less, I know that one will get negatively charged with more electrons, one will be positively charged with less electrons. They'll be opposite charges. And because they're opposite charges, they will attract one another. So the answer here is that they have opposite charges and they attract one another. And importantly, we didn't need to have remembered whether glass likes electrons more, silk likes electrons more. Okay. It's all a very nice story of electrical attraction and repulsion leading to electrical charges, positive and negative, as sources of attraction and repulsion. But think back to the ancient Greek observation. They rubbed amber with, say, cat's fur. They charged it up, and then they found it attracted straw or hair or feathers. They didn't rub the straw, the hair or feathers. They didn't charge up the straw, the hair or feathers. The straw, the hair, and feathers were what we would call electrically neutral. They got a balance of electrons and protons in them. So why was the straw or the hair or the feathers attracted to the charged amber? Here's the explanation. So over here on the left, imagine this is the charged up amber. And I've pictured it as liking electrons. So it's got an excess of electrons. And over here on the right, this is the straw or the feather or the some other light object that I can't remember now. They attract one another. Why do they attract one another? They attract one another, and it's a very important point. They attract one another because even that neutral object, the feather or the hair or the straw, is made up of charged building blocks. It's made up of electrons and protons, positive and negative charges. If this amber is negatively charged, it's going to attract towards it, through electrical attraction, the positive ends of the molecules or atoms inside the straw or the feather. It's going to repel the negative ends of the molecules or the atoms inside the straw and the feather. So that's what I drew here. I deliberately drew the positive ends of all of these blue molecules closer to the amber. I deliberately drew all the negative ends of the molecules further away from the amber, because the positive ends are being attracted, the negative ends are being repelled. Now, this means that the positive charges in the straw, the feather, or the hair are a little bit closer. They're a tiny bit closer to the amber. The negative charges are a little bit further away from the amber. The amber attracts the feather or the straw because the attraction of the closer positive charges actually wins, is slightly stronger than the repulsion of the negative charges, the slightly further away negative charges. This observation is actually telling us an incredibly important thing, that charged objects attract neutral objects. Tells us a very important thing. Firstly, it tells you that neutral objects are made of charged building blocks. Inside them, there are charged building blocks. So that's very important. It tells us that all matter is built out of charged building blocks. It also tells us a very important second thing. It's kind of I didn't think about this till now. It's foretelling our next class. It's foretelling Thursday's class. It's that the electrical attraction or the electrical repulsion between charges falls off, which means gets weaker with increasing distance between the charges. We can tell that because the attraction in this picture of the positive charges is winning over the repulsion and the negative charges, because the positive charges are a little bit closer, then the negative charges are a little bit further away. So we're seeing the fact that the electrical interaction falls off, decreases with distance between charges. And that's a story, that's foretelling the story that we're going to tell in Thursday's class about electrical forces. Okay. I have a feeling I missed a slide, but I don't think I have missed a slide. But I can't get back to the one I want to be in. Okay. You know, I want to talk about dimensions. Yes?
Going back to the previous slide, let's say if you flip the straw, would it just start repelling instead, or would it just still...
If you turned it around? No, I think it just rearranged to make sure again that the opposite charged parts are nearer and the like charged parts are further away. So I think you turn it around, it'll just change all the arrangements of its atoms and molecules. It'll still attract, yeah. That's an interesting point. I want to talk about dimensions of nature. So you met dimensions of nature in Physics 2:11. Space is a dimension of nature in which we live. Time is a dimension of nature in which we live. And mass is a basic dimension of nature, a basic property of materials. So in Physics 2:11, basically you worked with 3 dimensions. You worked with space, time, and matter, mass. Those were the dimensions of Physics 2:11. Everything else, all the other concepts, were built on those basic dimensions. They were kind of the irreducible dimensions. You can't break space down into some smaller bits or understanding. Can't break time down into smaller bits or understanding. So those are the basic dimensions of Physics 2:11. Physics 2:13 is about adding one more dimension of nature. And the dimension of nature, the property of nature that we're adding is electrical charge. So we've just discovered electrical charge, and that's what this whole course is going to be built on. All this stuff about electricity and magnetism and light and atoms and molecules, it's all going to be built on the fact that there is a dimension of nature that we call electrical charge. And so we have to really thank electrical charge because it's responsible for the periodic table, it's responsible for cells and neurons, it's responsible for hearts and brains and you and I and everything around us. Without that dimension of nature, there'll be nothing like that. And so I guess it's important. As an analogy, I'm a big fan of Martha Stewart, especially after she went to prison. Somehow for me that was, anyway. In home baking, right, there's some basic ingredients. And I might be getting this wrong, but I think you need flour and eggs and salt and milk, and maybe we should put in sugar somewhere. Those are the basic dimensions of home baking. Space, time, mass, and charge are the basic dimensions of our physical world. In both cases, right, the flour, etc., are what you make all the different types of cakes and baked goods out of. In physics, the space and time and mass and charge are what we're going to make all the different goodies out of in Physics 2:13. Okay, so we mentioned, now I want to move on to just a few comments about matter being electrical, matter being made of electrical components, electrons and protons. So we've realized now that matter is made of electrical building blocks, and actually there are 2 classes of matter that have distinct properties related to their electrical building blocks, and their names are conductors and insulators. And of course you know a bit about conductors and insulators. So this goes back to 300 years ago now, the discovery of 2 classes of materials according to their electrical characteristics, their electrical properties. Stephen Gray was an English pensioner, and I think he did this like in his bedroom as a hobby, and he figured out there are 2 classes of materials, insulators and conductors. And the whole of our modern world is built on an understanding that there are 2 classes of materials, right? Insulators and conductors. We have conducting copper wires, and then we have insulating plastic around those wires. So he gave us all of that, and it came out of his bedroom when he retired. So again, this was a world when you could make huge scientific discoveries in your bedroom, basically. Okay, so conductors. In conductors, charge, which often means electrons, but not always electrons, could mean ions, can flow through a conductor, can move through a conductor under the influence, under the effect of electrical interactions. So they conductors allow charge to flow through. You know, metals are the famous example of conductors, but also seawater is a good conductor. Lots of other solutions are good conductors. If you have a solid conductor, so a piece of metal, and you rub it, you've rubbed the metal, because it's a conductor, that charge that it acquires can spread out throughout the conductor, and it will spread out. It'll distribute itself through the conductor. So that's an important characteristic of a conductor. When it gets charged, the charge can move around and distribute itself. The other type of material is an insulator. So in insulators, charge, the electrons say, or maybe if it's a fluid, the ions, they don't flow around through the material. Charged ions or electrons don't flow through the material. That's what we mean by an insulator. And the famous examples of insulator are glass and plastic. So the glass rod and the plastic rod that I was charging up by rubbing them with silk or rubbing them with fur, they're insulators. So that when I charge them up, that charge that I create on them stays where I created it. It doesn't move all along the length of the plastic or the glass rod. So that's a fundamental difference. Okay, now I want to show you some technology, the very first electrical technology that was developed. It's going to be pretty basic technology. We're going to talk about more technology, how we generate electricity, for example, in later classes. But I want to show you, with this discovery of electrical attraction and electrical repulsion, and this idea of electrical charges, positive and negative, being the source of attraction and repulsion, people wanted to experiment with electricity. In particular, they wanted to harvest. They wanted to harvest charge, right? When I was rubbing the plastic or the glass rod, I was kind of harvesting some charge, collecting up some charge. But really, we want to more efficiently harvest some charge, to collect up the charge so that we can experiment with it. And so I want to show you a couple of devices related to that. This one over here, on the left, this is called a Van de Graaff generator. This one over here on the right, this is called a gold leaf electroscope. The one on the left, the Van de Graaff generator, is a device for literally harvesting charge, for collecting charge. And the one on the left, the gold leaf electroscope, is a device for measuring charge, detecting charge. And so if you were, imagine you were a scientist 300 years ago, you're really interested in electricity, you're going to get yourself one of these Van de Graaff generators, and you're going to get yourself one, here it is, gold leaf electroscope. That's what you want in your lab. So I've got this is, now you're looking at me here, I'm like an 18th century scientist working in the lab with these devices. So I want to show these to you, and I want to show you a couple of examples of the ways that you can charge things. The Van de Graaff generator, which is this device here, the way it works is instead of me rubbing a piece of plastic, piece of glass with cat's fur, there is inside here a belt that's connected to a motor that does the rubbing for me. Now I'm shining it in your eyes. So in here is a belt, and this is going to go around and round and round, and this could build up the charge. So that's how we harvest charge in a Van de Graaff generator. And then this device over here, this can measure charge. What you do is you place the charge on this plate upstairs here. This is a conductor. So the charge spreads out over this column here, this rod here. Everything becomes charged. Negatively charged if I add electrons, or positively charged if I remove electrons. There's a solid arm, this thick vertical arm. There's also a flexible arm, a movable arm these two will repel one another if it's charged. If it's charged, they'll either both be positive and repel. If it's charged, they might be both negative and they're also repel. So this device measures charge. So I want to show you these two guys. Oh, what's happening here? The belt is charging up the metal. The electrons are spreading out over the metal sphere. The electrons are getting onto the little hair. We're charging up the hair. The hair is all becoming negatively electrically charged and is repelling one another. So you can see here that I'm really able to harness a lot of electrical charge, way more than I could do by rubbing the plastic rod with a cat's fur, etc., etc. So this is a great device for harvesting charge. I'm going to collect some of it. I'm going to take some of it. So I've got another sphere here, right? If I put them in contact, this sphere will collect some of the charge. It's in contact. And that's called charging by contact. So I grabbed some of the charge. I wish we could see the charge. I wish it was like shiny blue or something like that and you can see it. But we can't. But I can move it over here and it doesn't work because it's wet today. Let me try again. Ow. Well, it's at some sort of angle. I want to show you this becoming electrically charged. But as I say, the demon for these demonstrations is wet weather. And we certainly have wet weather. I'm neutralizing it now. I'll give it one more go. I charged it. Okay, well, what you've got to imagine, let me show you I anticipated this too. God, every time you touch this, you get a shock, which doesn't help. I wanted to show you these two circumstances. This is charging by contact. So this is the electroscope, this is the generator, this is the electroscope. I was trying to pick up the electrons that I've harvested on the generator, pick them up on that metal sphere, and I was going to carry them across, depositing them on the electroscope. The electroscope would get some of these electrons, and you'd see the charge, because the flexible arm of the electroscope would be repelled by the solid arm of the electroscope. So this slide here is what I was trying to demonstrate. This is charging by contact. I had contact here, I had contact here. It's charging by contact. I couldn't do it, as I say, because it's wet. There's one other slide I wanted to show you. This is charging by what's called induction. So again, generator, electroscope. I'm harvesting electrons here. I'm collecting some of them here by charging by contact. Now I've just put the metal sphere close to the electroscope. If I put it close to the electroscope, then because the sphere is negatively charged, electrons on it, it repels the electrons. They run down the arms of the electroscope. And so you also see repulsion here. So this is charging by induction. In this case, the net charge on the electroscope is still zero. It's just got a positive end and a negative end, like a neutral object. In this case, the whole electroscope was negative because I transferred charge to it. So these two examples are examples of the, that are involved in the attraction of light objects or unlight objects, or the attraction of neutral objects is due to charging by induction. Anyway, I'm going to end there. We'll meet again on Thursday. If you've got any questions, I'll hang up here for a bit.